Now I'm really excited to present a fantastic speaker today, and also professor at UT Austin. He's somebody who's worked with the Department of Defense in the past and is exploring what it looks like for us to really work in low level orbits, and is doing research in space. So with no further ado, I will hand it over to Moriba Ja.
Yeah, thank you so much. Glad to be here with everybody, and I figure maybe I'm a bit different than what people see at Fed Supernova. So I will share my screen, and of course, this always works all the time. So let me try to do this really quickly, and hopefully people can see what's going on here. And if anybody can just give me a yes, that'd be great. Can people see that? All right, excellent. So look, the near-Earth space domain is a complex system. What I mean by that is that we see an emergence of behavior that is not explained by the superposition of individual behaviors of participants. We have a space environment that is dynamic, gravity, solar flux, charged particles, that sort of stuff. And the relationships and interdependencies of all the things in that environment are not fully understood. We see non-causal, we see non-linear causal relationships, right? So small causes can have huge consequences and effects. The objects that we put into Earth orbit, they are interacting with the space environment in ways that we can't always understand or predict. And on top of that, we have a number of growing participants, not all of which are well-intended in terms of their behavior on orbit. So we have genuine threats, and I'll talk about that a little bit further soon. I've heard lots of people say, oh, well, but space is big. What's the problem? Space is big. It's like, well, yeah, space is big. One might even say space is infinite, but the space around Earth used for putting, satellites that are providing any number of useful services like position, navigation, timing, financial, transaction type activity, even monitoring for human behavior on the planet, climate change, that sort of stuff. So where we put these satellites actually is finite. We only have specific orbital highways, orbital zip codes where we put these things. And so what I'm showing you here on the right-hand side is basically, some snapshot of about 4,000 of these satellites or objects in space. And I'm just mapping their locations in space and their velocities to the space called specific orbital angular momentum. And that's what you see. You see these kind of rings or these highways. And the interesting thing, right, is that the color is based on the inclination of their orbit with respect to the equator. So 0-degree inclination are things that are orbiting about Earth's equator, and things that would be 90 degrees inclination would be things that would be going over the North and South Pole as they orbit the planet. And so you can see I haven't done any sort of clustering analysis to this, but these things naturally kind of fall or segregate based on this inclination, and the energy of the orbit gives you the height of the dots in this plot. This is all to say that you can see that this isn't just uniformly, it doesn't look like a random pattern right here, right? It doesn't look like randomness. It doesn't look like white noise. There's structure to this. And so the highways that we have in space have structure to them, and they're finite, and the carrying capacity of these things is getting more and more saturated. So one of the things that we want to avoid, amongst other things, is we want to avoid harmful interference. And that is to say, we want to avoid the loss, disruption, or degradation of space services, activities, or capabilities. And even we want to avoid the detriment to science like astronomy. And I'll talk about that here in a little bit. So we're interested in knowing about the entire population of these human-made objects or anthropogenic space objects. That's what ASO means, anthropogenic space object, human-made, human-derived. We want to know about the entire population. But if you want to know something, you have to measure it. And we can't measure the entire population, okay? We can only measure a subset of it. And the subset of the population that we can measure, which I'll get to here, is the following. So we hypothesize there's probably about 1 million or more of these anthropogenic space objects that we need to be worried about, ranging in size from a speck of paint all the way up to the space station. But we can't track things as small as a speck of paint. We can only track things as small as, say, your cell phone. And so from that about, upwards of 1 million or 1.5 million, again, we're hypothesizing that based on the stuff that we can track and measure, which is roughly about 30,000 objects, again, ranging in size from cell phone to the space station. And of those 30,000 objects, there's probably about 4,000 of these that actually work. They're providing some of these services that I described to you earlier, and everything else is garbage. Yeah, so basically out of the entire population that we hypothesize, we believe we're only tracking about 1% or so of that population. And of that percent, there's probably like 5% of the percent that we can track that actually works, and everything else is garbage. That's a lot of trash. What we've done to the land and the ocean and the air, we are definitely seeing that sort of behavior, that ecological unsustainability showing up in space. So here I say, et unum pluribus, which is kind of turning our own motto kind of over its head, meaning from one, many. So one finite environment, many different needs, competing needs. Space safety needs are, we're trying to avoid hazards, things bumping into each other. When two satellites collide, bad things happen because now that breaks up into many, many other pieces, and that in turn becomes space garbage. From a security perspective, and certainly the Department of Defense has a lot of interest in this, but also commercial needs. We want to mitigate escalatory behaviors and threats, and I'll talk about threats here in a little bit. We want unhindered use and access to space, and we're finding that we don't really have that anymore. And from a sustainability perspective, we're looking at things in terms of the sort of ecological sustainability, representing near-Earth space as an additional ecosystem to land, air, and ocean. So we want to say and space, okay? So in terms of sustainability metrics, talking about the carrying capacity of any given orbit, for regular ecosystems, we can define a carrying capacity above which undesirable things happen, like famine, pandemics, these sorts of things. Looking at highways, we can come up with a carrying capacity for highways to sustain safe traffic. So we can draw from that, and we can look at space, these orbital zip codes that I show you, as also having a carrying capacity. And we can think of that carrying capacity being saturated when our decisions and actions can no longer prevent undesirable things from happening, right? So it's like if we're trying to keep ourselves safe, not bump into each other and that sort of thing, and our decisions are not preventing that from happening above some threshold, then for all intents and purposes, we can say that the carrying capacity for that orbit has been exceeded, okay? So we want to be thinking about that. Part of a way to think about this carrying capacity is, just like we have a carbon footprint, let's think about like a space traffic footprint, and loosely understood as the burden that any given object places on the safety and sustainability of anything else. In other words, when I get in my car every morning, I turn it on, put it in reverse, I am now a burden to other pedestrians and drivers. And even though they can see me, and if they could even predict exactly what I'm going to do when, the fact that they have to account for my existence to keep themselves safe is a burden. And that's what we want to say with the space traffic footprint. So in this environment that is complex system, finite resource, safety, security, sustainability stuff, we have some concerns. For one, will space become all about securitization? And by that, I mean anything that we don't understand, should we just consider that a threat? I would say not. I think that's dangerous behavior to do, right? So our default action tends to be associated with this hypothesis that everything that we do, you don't understand, is potentially harmful. We have a technological arms race. We have an arms race in space. That should not be to anybody's surprise. So how do we disambiguate threats, which I'll describe here more in a little bit, from hazards? Okay, and I'll talk about that here further. And we want peace. How do we deter conflict? How do we deter malicious behavior? There are lots of hypotheses that are different from each other that explain the same evidence. So there's a lot of ambiguity. And, what do people feel threatened about? What is coming too close and that sort of thing? So this is me as a young enlisted person in the Air Force. I was a security policeman. I was a nuclear missile guard. And I was taught that a threat required the concurrent existence of three things. One, opportunity for something to cause harm, the capability for something to cause harm, and then the intent for something to cause harm. Opportunity and capability are things that can be measured with physical sensors, radars, telescopes, these sorts of things. Intent, not so much. So that's one that we have to worry about. How do we actually measure or infer intent? How do we do that? And that is of concern. And I would say the difference between a threat and a hazard is that the hazard has the opportunity and capability to cause harm, but doesn't have the intent. So I'm saying difference between threat and hazard is really intent. Some practices that we could put in a place to help us kind of allay this intent piece, right? This thing that's ambiguous as to a threat, is development and maintenance of multi-sourced information, something like a digital commons, a digital library, a digital twin of the space environment, so that we can better understand and predict what's happening on orbit, and develop a body of evidence that we can use to hold people accountable for their behaviors. Monitoring, verification, and assessment of ASO behaviors. We want to be able to do more of that as well. Coordination and planning. Hey, I'm going to maneuver my satellite next week. I'm going to be within 100 kilometers of you. Just FYI, kind of thing. And look, the understanding, the technical understanding, the knowledge base for how to operate in space is not even across humanity. Different countries, different cultures have different notions and expertise. And so if the knowledge is uneven, the practice is definitely uneven. And it's the uneven practice that makes things kind of go awry. So what we want to do is, there's the need for capacity building. Let's level the playing field in terms of the knowledge base. And if we can make the knowledge more common, then the practice will become more common. And then last, we need to verify that people are complying with space laws and treaties and these sorts of things, and make that very transparent. So I talked about the things that we need, right? Our work needs to do three things, right? Make space more transparent. What is it? Who does it belong to? What can it do? Predictable. What's happening over the next few hours, days, weeks? What are any two given state actors going to do in a common scenario that has some cultural undertones to it as well? And then accountability. Can we develop a body of evidence to hold people accountable for their behaviors? I like to think of kind of the risk of space domain awareness and the knowledge that we have to make these decisions as being compartmentalized in terms of, dare I say it, known knowns, things that we are aware of having measured. And again, to know something, you have to measure it. Known unknowns, things that we are aware of not having measured. So we need to ascribe uncertainty to those things to account for our ignorance. And then unknown unknowns would therefore be things that we are unaware of and we have not measured. So these are enigmas. And so that brings me to the critical importance of big data, is being able to take massive quantities of disparate sources of information, heterogeneous information and data, aggregate these things, and then pose interesting questions of the aggregated data set to see if we have an unknown known. That is something that we are unaware of having measured. And so this is where discovery can come into play, data mining, that sort of stuff. Have we measured something quantifiable in the mutual information content of this aggregated data set? Again, the knowledge base is uneven, so the practice is uneven, and something that helps harmonize these things is a set of values that we can apply that we can all agree to. One of the things that we use in the space domain is this thing called the UTA Loop, developed by John Boyd in like the 80s. And basically it stands for observe, orient, decide, and act. I think a lot of people basically go from observe to decide and act. That's not so good. So what we want is we want to focus on this orient piece, because observations by themselves aren't so useful. I told you that multiple hypotheses could explain the same evidence. So when your satellite stops working, was it because Jimmy schwacked your satellite, or did the sun have some hiccup that caused some single event upset to your onboard electronics? You know, that is not easy to disambiguate. Detecting versus tracking. People think that sensors by themselves, that's all you need. And that isn't all you need, because sensors just sense. Sensors do the detecting part. Sensors don't track anything. The tracking is the logic behind the output of the sensor. The tracking, those are the algorithms. It's the data science aspect to this sort of thing. So tracking requires detecting and ascribing identity to what you detected. And that's trickier. Said yet another way, most of the objects in space are not transmitting their own identity. And so we have an identity crisis. From buckets of disparate sources of information, we need to find a way to effectively aggregate these things and solve that identity crisis, solve the inverse problem. Given all this evidence, what generated it, right? To know something, you have to measure it. So starting from the far left, these are kind of a list of things that we can measure. So what combination of these gives us insight into physical characteristics of these anthropogenic space objects? And what combination of those gives us insight into functional and operational characteristics? And can we move even further to the right to come up with a trait-based classification or taxonomy that allows us to uniquely identify these objects? I told you that astronomy was negatively impacted by light pollution, by some of the objects that are on orbit, okay? So really what I'm talking about is this. Let me kind of show you. So sunlight is being reflected off of the objects towards the ground, towards astronomers. Here's a quick movie that I want to show that gives you an idea of this light pollution. This is happening on a nightly basis. On the left here, what you're seeing is if you're at the telescope looking straight up, the streaks are light being reflected off of the population of anthropogenic space objects. We're going from dusk to dawn in this movie. And so the objects haven't disappeared. It's just as we go further into the night, these objects are going through Earth's shadow, so they're no longer reflecting as much light. You have less number of objects reflecting light. But you can see that as we go towards dawn, that you see the swarm kind of show up again. And so this is what astronomers have to try to pierce through to get astronomy, to get real kind of physical science of stars, nebula, all these other interesting things, right? This is the level of clutter on a nightly basis that they have to deal with. And it's not getting better because, guess what? We're not going to stop launching satellites, okay? We have to guard ourselves against confirmation bias, the tendency to basically disregard evidence when evidence is telling you you should be surprised. That means that what you predict and what you observe are not identical. That is telling you that you should consider changing your belief. And inertia to doing that is confirmation bias. There's no single source of truth, okay? The truth about all sensors is all sensors lie. So the question is, how can we then amass and aggregate disparate sources of information to get to a picture that is more holistic, more comprehensive, that is truer? Case in point, if you look at the public truth from the US on where objects, a snapshot of like a Waze for space traffic, you might see something like this. But if you ask the Russians the same question, you might see something like that. These things are not identical. In a great part, they don't overlap. Who's telling the truth? What can you trust? What can't you trust? Even opinions on where one object, a common object, is located, ask 4 people, you get 4 different opinions. Are these things statistically consistent? How far apart are these? If you're going to say, watch out, you're going to bump into each other, which one? Opinion 1, 2, 3, or 4? How do we find the barycenter of these opinions to basically achieve some sort of consensus in understanding what's on orbit? How do we monitor for these threats? How do we do this independent verification and validation, and then maybe use that as a mechanism for deterrence? Roles for citizen science to help out in all this stuff. So one of the things that we did, there's a treaty on space object registration with the United Nations, and we came up with a ranking system because basically the treaty says register your object with the UN as soon as it's practicable. Okay? As soon as it's practicable. From the time you launch it, register it as soon as it's practicable. We decided to measure that. How are people interpreting that? And turns out that some countries, on average, interpret that to be 2 to 3 years after the thing's on orbit is to send the fax to the UN or whatever. My guess is that when they came up with the treaty and those words, they didn't mean, think about it for several years before you turn in the stuff. So the thing is, different cultures have different interpretations in how they implement this stuff. And before we start saying we need more laws in space, let's understand how people interpret and implement the current ones. And then once you have the measurements, you can't manage what you don't know. You don't know what you don't measure. Then we can have conversations about what is the intent of why we have the law, and can we do something more common to achieve that? So what I'll do is I'll leave you with this quote from Rudolf Emil Kalman, the co-inventor of the Kalman filter, which is, whenever a model is built, it's always proper to ponder the basic scientific question: is the model really based on the data, or is an artifact displaying the prejudices of its creator? Thank you very much.